Okay. So, welcome. My name is Professor David Parent, and I am your EE 110 instructor and your EE 110 lab coordinator. And rather than um, just do the old miss the first lab while everyone gets their act together routine, I thought we'd have a review of EE 98, which the skills in EE 98 or your introduction to circuit analysis course. Basically, how well you've mastered those skills is probably the biggest predictor of how well you'll do in 110. So it's also, if you were like me as a college student, you probably spent the summer working at a job probably unrelated to EE to save up enough money to make it through the year. So it's some of these topics, you know, we all might be a bit rusty on. Um, but I just wanted to know that I'm really excited to teach you and I'm glad you're here. Um, Usually I'd like to, in a smaller class, I'd like to have everybody check in, but at 32 and class actually is 109, it'll be hard to do, but I will come up with some class activities that we can do where we can all learn how to make friends. And, making good study friends is probably the second most important thing you can do to succeed um, at San Jose State. But before we get going, are there any questions? And you can put them in the chat too. Although I must say, sometimes when I start really getting into a topic, I don't really see that there's a chat. Or so sometimes if you really have a burning question, you just kind of have to interrupt me, and that's okay. Okay. So I've actually created a review document in Google Docs. Let's see, where is it? All right. And you already have access to this, but you just might not know um, where it is. And what I'll do is put it in the chat. Okay. So I just saw your question. Let me. Okay. So someone has a question. Many of my classes haven't created a Canvas page and there's no building named on the class sign up page. Is there still confusion for some classes whether they'll be online or not? Well, and yeah, Carson, I think there's confusion, that's for sure. But no, every class will either be online or face to face. However, online, it won't say online in your sign in your course schedule, right? It'll say hybrid, right? Hybrid really means online. And there was a legal reason why they say it that way, but everyone was supposed to have their Canvas page everyone was supposed to have a Canvas page and they should have emailed you the Zoom link, right? So yeah, like Brandon says, if the classroom is TBA, it'll be online, even though officially it'd be called hybrid. Um, I suggest, a polite email to the professor. And if it's, if you don't get a response, if it's an EE issue, I would email the chair. And what I mean is email the professor first, right? To give them a chance to respond, right? Because yeah, if your class doesn't meet till Monday, they're probably going to do it over the weekend. But if you're not getting any joy about what is the Zoom link, right? And it's an EE class, that's the email of the chair. All right. Now, yeah, just to, even though it's a review, so like this is my Canvas shell, which you guys have probably seen. And yeah, right at the top, there's the Zoom link for the for 110, right? Um, and yeah, there's been this weird thing where there says there's been meetings, and it's not true. Nothing has started until Monday. I think what it is people are logging in and logging out just to check whether the link works or not. And it's maybe giving you all a message. And I know that there's one of these videos that somehow got turned to private, and I'll fix that. But if you want to see where this review is, it's right here, draft review notes. And in fact, they're less of a draft now, and I'll just call them. Now, I like to use the word EE98 because it's a lot faster to say than Introduction to Circuit Analysis. But again, all the classes should be equivalent for community college and San Jose State. And in fact, at the ENZA, one of the instructors teaches in both places, here and San Jose State. All right. Let me see if I can. Yeah. Okay. That's a good question. And anything else before we get going here? Okay. So let's just talk. So the thing is we learn a lot of things in EE98, right? And it can be a bit overwhelming. And there's so many tips and tricks and ways of doing things that you can get really confused, right? There's things like voltage division, Thevenin, mesh, and nodal analysis, right? And there's just these various ways of doing problems. My suggestion is to use the easiest thing first, right? Which tends to be voltage division. Thevenin can be important, but not necessarily used on a day-to-day basis. And which one is easier, mesh or nodal? You kind of have to look at the problem. All right. But they all depend on, the first thing you probably learned was, a resistor. And we learned Ohm's law. And the real thing that I struggled with is when I was learning it is that you have to make sure that your definitions are consistent. So if I say that's my current direction, right, then my voltage drop is here. So there's VR and IR, okay? And so that then when we have Ohm's law, right, that works, right? And so, if I had another resistor here, right? And I say the current is going in that direction. And now I'm just going to call it I, right? So if the current is going in that direction, I have to put the voltage drops from positive to negative in this direction. And that would be VR. And still, VR equals IR, because now I labeled that IR. All right. And so that's like the kind of the fundamental thing, right? Um, and now I'm going to kind of push the envelope just a little bit. And what happens if I have a current direction, but now I have it opposite, right? Well, V will now equal minus IR. And this comes up more in EE 122, all right, when you have behavioral current sources, but this can happen. And so what do I remember from 98? It doesn't matter how you assign it, as long as you're consistent, you'll always get the wrong, you'll always get the wrong answer. Excuse me. You'll always get the right answer. But the thing is it's probably better to always draw it the right way, right? Or a way that makes physical sense, because if you're drawing an arrow one way, right, but forgetting the voltage drop goes the other way, this is mathematically correct, but it's a little counterintuitive. So you might, get the answer wrong. So it's really important to always put the current directions and the voltage drops across the resistance um, in the proper direction, if you can. All right. Now, this isn't really a 110 topic, but if I have a current source, okay, right? Well, and I call that ground, and I'm just going to give that a label D. Well, that current, right, it's forcing the current this way, right? So you'd have a plus and a minus, and we can just call that R, right? So it's true. VR, we'll just call that I, equals I R. However, VD is not equal to VR. VD is measured from this D node to ground. And so it's a nodal type definition, right? So I put the positive end of my ohm meter or voltmeter here and the negative end here, and I'm going to get actually VD equals minus IR. Now again, that's more 122. And I kind of went over kind of like a mesh and a nodal all at once, just jumping in there. What you need to remember, though, is just to really keep a track of where those positives and negatives are. Any questions so far? Or I'm going to check like I said, I don't know what it is with my account, but the chats don't seem to give me a notification. All right, so anything so far?
No.
Okay. Okay. Now, so that's our resistor, right? Well, actually, this holds true for our capacitance, right? If I have the current direction there, right, I have my voltage drop there, and it holds true for an inductor, all right? And sure, these have differential equations associated with them, all right? But really, what we do is we look at impedance, which assumes there's a sine wave input, okay? And what we can do is ZR is resistance, right? The impedance of a resistor doesn't change with frequency, but the impedance of a capacitor does. Same with an inductor, okay? And so this R is the R that you read, you know, with your colored stripes. That's whatever you read printed on the capacitor, and same there. Those are the values of R, L, and C. All right. And let's just have a quick review here. What's J? J is the imaginary number. It's the square root of -1. Okay. And this is frequency in radians per second. All right. So there's only one frequency here. So the only waveform that only has one frequency, you know, is a sine or a cosine wave, which they're really the same. They're just delayed. Okay. So that's pretty easy to write. It comes from, if you want to look up in your 98 textbook, right? Phasor analysis. Okay. And but you can also take the Laplace transform of these current voltage relationships and then take the ratio, right? And then you get these impedances. Now, the important thing about that, and that one step, right? I assume there's a sine wave, right? With just one frequency. Now I can use impedances, right, to analyze my circuits. Now, let's take a step back, right? Can anybody tell me what the equivalent resistance is of this network from A to B? Meaning I'm putting my ohm meter, right, and connecting it between here and here.
Would it just be the sum of all the resistors?
Yeah, that's a great way to put it too. I would have said it's R1 plus R2, R3, R4. But yeah, R equivalent equals the sum of Rn, what, 1 to 4, right? You just sum it up. And why? And they're because they're in series. And what you noticed is that they were in series. And how do you tell it's in series? Well, you just say, I'm a current, I'm an electron. Now, of course, the electron's going opposite, but in circuit analysis, we assume positive charges. So I'm moving along. I go through R1, then I go through R2, R3, R4, and I come back. There's only one path, right, to get through an element. So they're all happen to be in series, right? Now, yeah, if I had this, right? Oh, R1 to R2, those are in series, but now I have a choice of which way to go, right? The current splits, but in a way, it's kind of like a trick question. The current splits in two directions, then comes back. And so in fact, these three are in series, you just don't notice it. Now, yeah, I can take let's find a prettier color here, right? I can find the equivalent resistance of that and get, the parallel combination, right? Well, let's say I had, this network. I just label it Z equivalent, right? And Z equivalent is going to sum up all these various capacitances. So I don't know if you were like me, but you might think, well, capacitances in series get combined like they're in parallel, and capacitances in parallel combine like they're in series. And it's just like one more rule to remember, right? Well, it's true, but essentially, right, I would have 1 over SC1 plus 1 over SC2 plus. And so, right, the equivalent, right, because the impedance is 1 over this. So the equivalent is really, yeah, they're all 1 over. And so to add them up, right, you would end up, I mean, either you just find a number or, and then it's just a easy sum. But you can see that to come up with an algebraic equation, you'd have to find the common denominator. Okay. And so, same thing with the inductance, right? But let's move on to a parallel combination, right? What's like the effective equivalent impedance of this network?
Is it 1 over L1 plus 1 over L2?
It's close. The what if I ask this? How would you modify it?
Say R1 times R2 over R1 plus R2.
Right. right. Or you might say R1 in parallel with R2, and however you calculate it, right, would be however you calculate it. So in fact, it would be ZL1 in parallel with ZL2. Just let me move the chat, right? So it's the same relationship, right? So now what's excuse me, SL1, because that's the impedance, SL2. Now, because there's only two elements, we can use this, right? But the important, or I should say, like, it's really just R1 plus R2, R1 times R2, R1 plus R2. And yeah, because this is a frequency dependent component, right? Because S equals J omega, right? So that's ZL equals J omega L, right? The higher the frequency, the bigger the impedance, right? The answer has to have frequency in it, right? This had no frequency component, and so you could just do it like that. Now, this is where it gets, maybe more useful is, or you can see the power of it, I should say, is what if I had a parallel combination of all three elements, right? I could, without getting into the weeds of it, right? Z equivalent is really ZR in parallel with ZC in parallel with ZL, right? So now this just becomes an algebraic exercise, right? But you can see that all these elements are in fact in parallel, right? And let's just do a quick review on, parallel, right? If there's more than one way to get to 2 points or 2 nodes, right? I'm going from A to B, and there's more than one way to go, right? That element would be in parallel. So if I can come through this path, right? That's one. I can go through that path. That's another path. And I can go through here, right? And then while we're here, right? I'm drawing these components as if those are wires, but mathematically, I'm gonna draw that. Okay. These are all the same node. They're all the same voltage. Now, yeah, to build a circuit, those would have wires and they would, they have a distance. These, in fact, this is all the same node. So in some ways, if I just say, here's a node, right, I could redraw this. Okay. And even still, it's not getting you might see that it's more easier to see that these are two nodes, but still it looks like I've got a tail there, right? That there's like the wire hanging off the component, but that's really not physical in this kind of analysis, right? Ohm's law is really an approximation or a simplification of Maxwell's equations, but it was really just it wasn't like a simplification of Maxwell's equations. It was just these relationships were noticed. And I know when I draw a resistor, it looks like it has, a length and a width, but mathematically, it's just a point, right? That has, the V equals IR relationship. Not, we just have to make sure that we don't forget that, because when you're really building a circuit, you could have a current loop and can cause certain issues. All right. Learning about that is E140. All right. So far, right, we went over, assigning voltages and currents on a passive device and a resistor, right? And it's also a linear device. But then we are able to switch to impedance and then apply that same mathematical tools, right, to the capacitor and the inductor, right? And the tool that we examined, or one mathematical tool, right, is resistances in series sum up. Resistances in parallel, use the parallel equation, right? So that's a tool, it's a shortcut, right? I could use mesh analysis to find that relationship. I could use nodal analysis to find that relationship. But that, remembering that series things add, right, and parallel things use the parallel equation, right? That is a trick. That is a shortcut, right? Which can be very intuitive when trying to understand what a circuit does. And so what will happen on job interviews, right? They want you to puzzle out the circuit, right? What's going on here? And you have to explain it. They don't really want you to start writing nodal equations or mesh equations and coming up with the answer. They want to see your thought process, right? And, job interviews are kind of personal and, one-on-one, or, there's 3 of them and 1 of you, as opposed to being in school where there's 1 of me and 100 of you guys. Okay. So rather than, is their answer right or wrong, which tends to be, college, they want to see you puzzle it out. And so recognizing these are in series, recognizing something's in parallel, and the fact that, all we have to do is go to impedance, right? We can use those same relationships. So we did series and then we did parallel, right? And then I tried to give a little bit about the assumptions that go into what these models are, okay? What the Ohm's laws models are. So that's what we've done just so far in a half hour. Here we go. Okay, so a few people they put some answers there. But yeah, any questions so far? Okay. So actually, I want to apply it a little bit. All right. Just based on what we've done so far. All right. And I'm going to draw a circuit. So here's the thing, V in here, right, is from positive to negative, and that's ground. So V1, which is measured from 1 to ground, is in fact V in. And V out is also equal to VC, which is also, because it's out to ground. So let's just solve this a few different ways. So let's draw a current, right, I, because I'm always on this path, right? There's only one path. Everything is in series. There's only one current. So I can just write a loop equation, and I'm just going to call that Vn, right? And so we come along and it's minus Vn. Okay. I've assigned my loop direction current that way. And I'm just going to more carefully put my current directions, positive, negative, and that's going to be equal to VR plus VC, right? And I don't want to deal with a derivative or a time-based equation. So I'm going to switch to impedance and just say, oh, it's 1 over SC. All right. So VC.
Professor?
Oh, yes, sir.
I guess maybe I'm confused then. I thought if you're using negative V in, then it would be negative V in plus VR plus VC is equal to
Oh, God, yeah. No, you're right. And I would have figured it out eventually. Thanks. Yeah, I would have noticed it at some point. But thank you for pointing that out. I appreciate it. And yeah, what can happen is, yeah, when you already know the answer, it can be tough to slow down. But I know that anyway. So VC, right, is going to be equal to I ZC, and VR is equal to I ZR, right? And I'm just going to leave those there, right? So V in will equal I ZC plus I ZR. And so I equals V in here, right? And then what is V out equals VC equals I ZC, and I'll just call that, equation 1, and we'll call that, well, I'll call that equation 1, we'll call that equation 2, and we substitute, and we get Vn CC CR plus ZC. Okay. Now, which, if you look at this right here, is the voltage division equation, right? And so really, so let's say I'm on a job interview and they, can you, what's V out? Well, you could say, oh, voltage division, and it's the impedance of this divided by the sum of the impedances, right? Which is correct, but, or you can say, well, let me start writing equations, and you come up with the correct answer. But if you kind of describe, well, these are in series, so the current is common, the voltage will be distributed across these two, and the bigger ZC is, the larger V out will be, you know, probably would be better. All right. Let's do it again. Okay, but now let's do nodal analysis. So we'll call that out, and I'll just call that node in, right? So we have our ground, everything is with respect to ground, right? V in here, right? The node is known, right? Because in is measured from with respect to ground, with the node to ground. V in, yeah, we assume it's an ideal voltage source, so it can supply as much current as needed, no matter what's going on over here, to make that, right? So we already know that we know that node. Ground is the reference potential, and it's kind of set to 0. Why is it set to 0? It's not that it's magically at 0, but if I measure the voltage, right, V ground to V ground, right? I put a pot. I think I'm kind of echoing. I just hold on a second. Okay. So if I put the positive end of my voltmeter here and the negative end of my voltmeter here, right? Positive and negative, there is no voltage drop. So that's why ground is 0, right? It's not that this is magically at 0 volts. Remember, voltage is always between 2 points. But when we say V in, we really mean V in to ground. When I say V out, I really mean out to ground. Where if you say the VR, it's across the R. VC is across the C. All right. Anyway, so that node is known. That node is known. Here, V out, we don't know what it is off the top of our heads. So there's really only one nodal equation, right? And so we have something coming in and something coming out. And we'll just call that I1 and I2. Well, what comes in must come out. I1 equals I2. And that's our first equation, right? Now, what is I1 equal to, right? Well, I1 equals VR divided by R, right? But what's VR? We can't use the device name. We're doing nodal analysis. So everything has to be in terms of the node in, out, and ground is just never shown, right? Well, that would be V in minus V out divided by R. I2 equals VC divided by ZC, which is just V out divided by the impedance, right? So that's equation 2, 3. We put 2 into 3, and we get V in minus V out divided by R equals V out keep it impedances. Okay. And so after some algebraic manipulation, you're going to get the same relationship, right? Voltage division. So in these two methods, right, this nodal analysis took up a little bit more time than the mesh analysis, right? And the thing is sometimes you can't use mesh, sometimes you can't use voltage division. Nodal analysis is the most generic way. You should be able to find a solution no matter what using nodal, but sometimes it can be so convoluted that it'd be better to try to simplify it first. And so I know what it's like is you don't have a lot of time on your hands as a student. And if somebody tells you, you know, you can solve any problem with nodal analysis, then you say, well, then I don't need to learn anything else. It's not true because even in this simple case, you can see one method is easier than the other. All right. But here's the other thing is that now, right, we derived it, and I'm not going to write everything, right? But that we know that V out equals V in CC CR plus CC. Now, a little off here. So here's the thing. This is, that has a frequency to it. That has a frequency to it. And so V out to V in, that ratio is going to change depending on the frequency. Okay. And we don't actually, so here's the thing. What if, let's simplify it even more. We'll call this R1 and R2. Okay. V out over V in. So we're just taking that ratio. R2. So we have our voltage division equation. If R2, let's just say, gets much, much bigger than R1, right? This is getting bigger, this is getting bigger, right? Then that relationship is going to go to R2 over R2, or it'll get very close to 1, right? If R2 is much, much less than R1, right? This will get a lot smaller than that, right? And it eventually goes to 0, right? Because if there's no resistance here, well, it's effectively tied to ground, right? So then that relationship, you know, goes to 0. Now let's go and think of in terms of this. And this is actually a filter. So what's ZC if omega equals 0? All right, ZC 1 over J omega C, right? 1 over 0, it goes to infinity, right? So that impedance is going towards infinity, right? Well, that's just like this case where R2 is much, much bigger than R1. What I'm saying is ZC is much, much bigger than ZR, right? And so running a little bit out of room, but here's omega. And if I have 0 radians per second here, right, this relationship is going to 1, right? Well, what if What if omega goes to infinity? Z equals 1 over J infinity, right? ZC goes to 0, which means like that's a short. And that means at infinity, right? It's at 0. So this ratio of V out to V in is going down with frequency, and we call that a low pass filter, right? So rather than a phasor problem where you're told it's 60 hertz and it never changes, oh, I can break it up. What about 0 hertz? What about 1 hertz? What about 1,000 hertz or radians per second, right? This just gets smaller and smaller as we go, okay? Now let's speed it up. Okay. I know, right, they're all in series. All I've done is replace an inductor into where the capacitor was, right? So I know it's voltage division. And so I know the ratio is going to be this. Right? Which is SL R plus SL, right? Which then you could, put in your J omega right in there, right? But again, let's just think about it in terms of ZL if omega equals 0, right? ZL equals J omega L equals J 0L, right? Because this is just much, much smaller, right? So this will be much, much smaller than that. It'll be effective. This is small. It'll be effectively shorted. So here at 0, I'm going to be at 0, right? Well, what if what is ZL if omega equals infinity, right? ZL equals J infinity L equals goes to infinity, right? So now this is much, much bigger than ZL is much, much bigger than ZR, and the radiation goes to 1, which is a high pass filter. All right. So really, to sum up, right, we've used ZR, ZL, and ZC, right? And we've we've used our series thing, which then came to voltage division, right? Which gave us, some Z, right? And Z2, right? It's dependent on frequency, right? Capacitances, it goes down with frequency. Inductances, it goes up. And just by using that and letting omega go to 0 or infinity, we're able to figure out what is this filter going to do, right? And so you're already designing a filter, okay? Now, what does that, really mean is that if you're playing some music right? And you put it into the low pass, so if you're listening to music, you put it into the low pass filter, the high frequencies are reduced, right? So high pitched sounds, right? If on average female voices have a higher frequency than male voices, right? You're attenuating the female voices, right? And you're keeping like the baseline, right? But if you put that into a high pass, meaning it lets the high through, right? Low frequencies are reduced, okay? So it gets rid of that bass, right? Now, here's the thing. I was talking about one frequency, right? Music has a lot of frequencies. And something we'll be learning in 110 is that you can take any kind of signal, and as long as it repeats, you can find out what sines and cosines, magnitudes, and frequencies compose it, right? And so you can design your filters like that. Which is, kind of a lot of information. What I suggest is after this, kind of just review on your own, series, parallel, and do a few of these kind of examples on your own. All right, then you'll know if you really know it or not. Just listening isn't enough, right? You got to practice it. Any questions so far?
So what are we trying to learn in this class? Like,
Oh,
what is the goal?
110? What,
Yeah,
110 or today?
110.
Okay. Just so you know, right? This was a review of what you needed to learn to understand 110. What the class is about, right, would be covered later in actual class. But since you ask, right? And some things you might not understand the words yet, right? But one of the main things we're going to be learning are signals, okay? And a signal can be, a sine wave, and it can be electrical, it can be a pressure wave, it can be, whatever. Other signals that we're going to do are something called a step function, where it's 0 and then it goes up or down at a specific moment in time. And then another big signal is the ramp, where it's 0 and then it's ramping up at a slope, or right. So what we're going to do is take complex signals, right, and decompose them, right? Now, the reason why we do that is so that we can manipulate them, okay? And the example we already went over, right, is low pass and high pass, okay? So that was a signal manipulation, right? We're getting rid of a frequency band, right? Now, but then a big part, right, because it's signals, it's circuits and signals, right? But if you're looking for other materials, systems and signals, or signals and systems, however you want to say it. So the thing is how do we manipulate them? Well, right, this is a better low pass filter. Okay, and so that's an op amp circuit. So we learn how to do, this might have been something covered in year 98. We'll do this and learn more advanced techniques of filters, right? So, but not only, so we decomposed it, how are we going to manipulate them? Here's like a filter, right? So then another thing we have to learn, right, is I think we're all familiar with the time domain, right? Where the sine wave is doing something like that. We have to look at, we'll have to learn how to look at things in the frequency domain. Okay, where I kind of was showing where that was headed, where I had a frequency, I had 0, and then I had some infinity, right? So there's something called a Bode plot, which allows you to see what a system is doing or design a system a lot easier, right? So we have to be able to learn how to look at things in the frequency domain. And how do we get to the frequency domain? The Laplace transform and the Fourier transform. Okay. And again, the Laplace transform, though, yeah, S equals some real number plus an imaginary component, right? It's complex, right? And so its signals they don't have to repeat. I can do this. Fourier transform, all the signals can only be sine waves, and they have to repeat, and they have to repeat forever. But it's almost the same transform, okay? And this would actually lead to the Bode plot, right? And so, yeah, we first look at signals so that we all understand what a sine wave, square, step, ramps, and how they're related, right? How are we going to manipulate the signals in this class? Mostly via circuits, although you know, a big part of what we do is we put a signal into a system. What happens? Now, of course, sometimes we want something to happen to a particular signal, so you have to design the system, right? And really, we're just kind of do that again and again and again, right? But because we use op amps so much, we move beyond the ideal op amp, right? Where the op amp actually has frequency limitations. And we spend time on what are those frequency limitations, right? Now, there is a topic that we kind of sneak in where maybe it is if I take a mass, right, and a spring, and a damper, and let's say this is a platform and it's moving, right? I can convert this. I'm sorry, I know that color isn't that great. I should get better colors. I can convert this into a circuit, which now you notice everything is in series. You can find out V out using our impedance and voltage divisions. We can use our easily done Laplace transforms. We can do a Bode plot of how this would react, right? So all of these things can be done, with a circuit. And so I can simulate a mass, spring, and damper, right? And LT spice, right? I say, all right, here's my damper. Here's my inductor. Here's my capacitor, that's a mass. So whatever the mass is, I just convert it to farads. Whatever the spring coefficient is, I convert that to Henrys, and whatever the damper is, I convert that into resistance, right? And I can just, oh, what if now, rather than those, what if I have this, right? And you can use this tool to analyze everything. And this can be great for robotics, right? But even a hard drive controller where you have a disk, right? And you have the head, this is spinning, right? This has to move back and forth to read the data. That movement, right, is a physical system that has a mass. That arm has a mass, it has a spring coefficient, it has a damper system, right? And so you could simulate, verify, design things in LT Spice on just the movement of where that the head will be on that. That's probably all I can say, because 110, well, there really is, it's one of those transformative classes. Once you master the subjects, a lot of times you don't go back to the 98 way of doing things. You're transformed. It's one of those courses that makes you an EE, right? And and another way to summarize it is, after you take 110, your friends and family aren't going to understand you anymore when you start talking about what you're doing in school. All right. And so to go into it anymore, I just might be using terms that you just haven't seen yet. It's, it has nothing to do with intelligence. It's just, we really look at things in the frequency domain, and we design things in the frequency domain so much that we even forget about the time domain sometimes, right? But yeah, it's and so it's not just me saying it because I teach it, right? But 110 is the prereq for 122, 132, 160, 102, and 104. It pretty much unlocks almost all of the upper division undergrad curriculum. 112 unlocks a few things. 118 unlocks 120, which then unlocks some more digital classes. And your MATI 153 unlocks, your device physics. So now, yeah, I see the chat and I'm about to answer your question. I just have to say, right, that 110, the prerequisite is EE98 and differential equations. I'm not going to check, right? You're going to have to fill out a quiz to say that you've had it, and that if you haven't had it, you understand the the downside risk of trying to take this course without being properly prepared. All right. Just because and let's say you pass 110, it doesn't mean you don't have to pass 98, right? And I don't like using the phrase pass. I'd like to really you to excel in this class. It's really a powerful set of tools for looking at systems design. Now, I know that might have been a lot. Okay, I'll answer the 140 question, but I forget who asked that question of what is 110 about, but does that answer your question? That answer?
Yeah, for the most part, thanks.
Oh, what else is don't you get?
Well, I guess it'll probably just come down to experiencing it. Like, I was just wondering what a day would be like if we're gonna build our own circuits, or are we gonna like solve circuits like with the differential equations like we did in the last course or something like that.
So we're not going to solve circuits like when I say the differential equation approach, meaning, you know, dv dt equals something. No, we're going to rapidly move into the impedance into the way I was doing it, right? But it really isn't it's not a 100% extension of 98. Where we learn a lot of mathematical tools and to look at systems in general. Okay. Does that help?
Yeah, yeah.
Okay.
Thank you.
But I mean, you know, everything. All right. You want to figure it out? You can go click on my on the sample exams I have, right? So that could probably tell you maybe what you really want to know, or not to say you're only in it for a test, but that's what it's about. Okay. Now, yeah, Sawanji, yeah, 140 is pretty mind-boggling. The thing is like I was saying before, the circuit analysis that we do use in this class will assume Ohm's law, which means the frequencies are low enough that resistors, capacitors, inductors, transistors, everything acts according to Ohm's law. But when you start to do high-speed systems, right? And if we're going to be, so sorry, Peter, just so you know, I see your question. I'll just answer it in a second. Okay. So, oh God, I'm sorry. I lost my train. So when you're working in the physical high-speed area, right? When Ohm's law doesn't work anymore, that's where 140 is going to be really helpful. Like, right, what's the biggest thing right now? 5G, right? And believe me, the department chair knows, and I know EE 140 has a particular reputation. And because electromagnetics is, right, it's not easy. It's not easy for anybody. I do have some tips that if you email me, I can give you
Yeah,
of
I
what to study.
was talking to a couple of friends that have taken EE 140 in other universities, and they basically all say the same thing. It's just a hard class.
Right. Now, but here's the thing, right? Sometimes is you do how you expect to do. And many years ago, we had reformulated 140, and truth be told, it was too hard. Okay, it was. And it took us a few semesters to figure that out. But we did. But what happens is, you know, students talk, which is a good thing, right? Don't get me wrong. But then, so the reputation kind of stuck around. And then, too, you've really got to be engaged in this class. You have to kind of read up on things before you come in. You can't be afraid to ask questions. He will do anything for you, but you kind of have to engage. And the nature of the material is you just can't, and I've done it, right? That looks like a problem I've done before. Let me copy that procedure. No, you really have to understand the concepts to be able to apply it. And yeah, I was just speaking to somebody over the summer, and he felt that 140 really changed his life. But something that transforms you, right, is never easy. But he will spend all the time in office hours. And I know what it's like. You don't want to go to the professor's office hours because they might realize what you don't know. That's why I didn't go to office hours. I'm like, well, if I just quiet, maybe they won't realize how much I don't know right now. Right? No, really. The people who get, do really well in my classes come to my office hours. Right? There's extra credit and things like that. Yeah, Ruben, is the review over? I think that's about all I was going to cover for today. These other things I'm going to talk about, I'll have it recorded, and you can always just, if you got to scoot, you got to scoot, right? All right, so Peter, okay. So EE98, right, is really just a lecture, right? There was a lab that goes with it, EE97. And you really need EE97's content to do well in 118. All right. Now in 110 lab, yeah, next week you're going to learn LT Spice and you're going to learn Python, right? It would have been great if you knew it before, but you can recover. But building circuits, screwing them up and fixing your own mistakes, which is kind of like what EE97, the physical part you're talking about, that's really important. Now, maybe Peter, you can email me exactly what's going on and I can look through your record, right? This is probably not a public conversation, but the thing is if you have credit for the lab, right, then we'll have to figure something out to help you. You're gonna have to work a little bit harder, and you can excel. So it's actually 110 lab, probably not the problem. It's really 118 where you build things. And even though 118 is digital logic and 98 would be more resistors, op amps, and things like that, it's really learning how to debug, okay, is the important thing. For this class, if anyone, oh yeah, thank you, Charisse. I probably should have said that right off the bat. So when I said making friends is a great way to learn how to succeed in the EE program, the student branch of the IEEE is probably the third most important thing that you can do. It's a physical space in room ENGR 376. It's also a student club. We have engineers, practicing engineers from local industry come in and talk about careers. And they also tell you how to do things. Like we have people from linear technology, now analog devices, they'll come in and show you how to make a power converter, right? It kind of died due to COVID, but now we can physically be together again. And in 110, I'm gonna really try to make, even though we're still online, I'm gonna try to make it so that we all don't feel so isolated and lonely and we're all in it together so that we can all succeed at life, okay? Is that what you wanted to say? Oh, is there a Discord server for this class? I haven't set it up yet, but there was an EE Discord server that people put a lot of things on. I have to figure it out. Now, Jahai, hopefully I'm saying that right. maybe send me an email to remind me to do that, because I've never set one up, but you know, I'm sure there's a YouTube video on it. Ah, yeah, okay. Okay, so yeah, Peter, if you learn P Spice, you're gonna love LT Spice. You are just gonna love it. It's so much better. Now, yeah, if you never used an oscilloscope, you know, maybe we gotta, oh, you know, Charisse, maybe IEEE, we should have a meeting, right? We got to pick a day and say, all right, if you've never used an oscilloscope due to COVID, right? Let's come in and we'll learn how to do it. Now in 110 lab, we do have oscilloscopes there, and maybe in 110 lab, we got to come up with something extra on how to use an oscilloscope. But we're not going to make anybody retake a class. But like Peter says, he wants to make sure he's not behind. But we can figure it out. Okay.
Yeah, actually currently I'm trying to talk to the last president because I am currently the new president for the IEEE. So I'm still trying to figure out a lot of things.
What happened to Marielle?
I have no idea. Yeah, I'm still trying to find people to join and join the board as well. So if you're interested in joining the board, please let me know. Yeah.
Charisse.
Yes.
I thought, okay. I thought we had, oh boy. The previous president from last year, they're all gone. All those officers are gone.
Yeah.
So you're not going to find them.
Yeah.
But I thought we had a new IEEE president, Marielle de Guzman, who was working with the department chair.
Oh, I actually talked to Derek like this past summer to take over.
Okay, well,
I guess we'll talk another time about it.
No. This has to be no, because it's already.
Oh, because I emailed
It was great that you took initiative, but it's not just a normal student club.
Yeah.
And so, all right.
Yeah,
Please,
I already
know
like
that
emailed every like
right
and everything. Yeah.
Really, please, I'm retyping it. Please contact the department chair.
Yeah.
To find out who's really in charge, because I know we have somebody else who's actually controlling the Facebook.
Oh, okay.
Site.
Yeah, I think I'll clear it up as soon as I can.
Yeah. Anyway, it's all good. Oh, there isn't a room channel for 110. Oh, okay. So Jahai, you're talking about Discord servers. Here's the thing. It was one big EE department Discord server, I believe. And I never read it because I thought I wanted students to be able to write whatever they wanted to write and vent however they wanted to vent without me looking in. But what folks said is that it was so helpful that I should have a dedicated 110. And actually, it can be a 110 lab Discord server, right? So I was going to do it. I just hadn't done it. Okay. But thank you. All right. Anything else before we all scoot to the rest of our lives? Okay. So if I know this is 110 labs time, but I'm going to post this video in 110 and it'll probably be under Start Here, and I'll post it in 110 Lab. That way, is there any separate Tuesday meeting paper? There is a student fee for IEEE, right? But anyway, take care, everyone, and have a good weekend. And I forget who said it with the online screen captioning. I didn't know that existed. And so thank you for telling me that. Anytime, if I forget to turn it on, or maybe I can, and it seems really good as I'm reading it as we go along. So thank you for telling me about that. That's really an excellent tool, and I'll leave it at that. Oh, everybody's okay. So this time I'm really saying goodbye. Have a good weekend.
Thank you.
All right, bye-bye.